Well, welcome back, guys. All right, couple of things. I'm looking at the calendar and I'm looking at the chapters we have left. Today, obviously, is what the 22nd. We're going to start chapter 14. It's a little bit long, maybe take 2 days to do that. It's 30 some slides. The concepts there are a little bit more can be a little challenging. Okay, so when I'm looking, and then after that, we got chapter 15, which is a very short chapter. So the bottom line is this: it looks like we're going to have a lot of extra time, which like we did last week, as far or earlier this week, we did the study day. And I think I'm going to do that. So starting next Tuesdays until the end of the semester, we're going to make those days the study day. And some of you came in Tuesday and had some problems that I can go over. We went over them. It was, so it's a very good time to come in and ask questions about either the chapters we just talked about or anything else throughout the semester, because remember that the final is comprehensive, including, which means if the whole chapters 1 through 15. So if you should be preparing for that coming up and start looking at things in the past. And if start making notes of maybe things you want me to go over and maybe refresh your memory on and things like that. So come Tuesday, this coming Tuesday, and I'll send an email to that effect. And every Tuesday after that, until our final, which is the May the 18th. That is the final. So it looks like the 27th of April, the 4th of May, and the 11th of May would be study days. So that's 3 days. And then we have the 22nd, which is today. We'll do chapter 14, and then we'll continue with it next week on the 29th, chapter 14. And then the 6th of May, we'll start up with 15. Probably knock it out one day. It depends on, the questions asked, and maybe I need to go slow down a little bit, but probably finish it in one day. If not, we'll finish that on the 13th, okay, of May. So I'll summarize all that in an email, send it out to all the sections. So that gives you 1, 2, 3 study days, if you will, that I'll be here. We won't have lecture, but I'll be here and go over any of the questions that you may have. Okay. All right. And happy Earth Day today, by the way. Okay, so let's jump into chapter 14. Now, chapter 14 deals with what we call the letters of IMF, which stands for Intermolecular Forces. Now, before we begin this, I want to refresh your memory because this is something that you really need to grasp before we can get into this, okay? Now, let me open the whiteboard. Now, remember, there are 2 types of bonds that we had to deal with, okay? Which was Ionic Bonds, okay? And Covalent Bonds. Okay, with ionic bonds, there was a combination of a metal, non-metal. Okay, these were ionic bonds. Now, by the most part, most of these were soluble in water. Okay, so we had a full-fledged metal, and I'm just going to label that with some plus charge. Could be any value from +1 to, maybe a +3, okay? And we had a non-metal, I'm going to just label that N, terrible looking hand there. Let's see if I can fix that up a little bit. Okay, just to represent a non-metal. And that had a negative charge, which could be a -1, it could be a -2 or -3. Okay, these two got together, and as an attraction, what we call an electrostatic attraction, much like two magnets coming together, because you got the full-fledged, and that's important. We got a full-fledged charge on positive and a full-fledged charge, a full charge, negative charge on the negative anion, okay? Those are ionic compounds. By the most part, these guys were soluble in water, and the ones that were not, due to solubility, they were insoluble, okay? And if they were classified as insoluble, that did not mean that they did not dissolve. It just meant that a lot of the material remained intact as a solid precipitate, but there were some few ions in solution. It still conducted electricity, which reminds me, water in its pure state does not break up into the ions. It is a non-electrolyte. Pure 100% water does not conduct electricity because there's no ions in there. And so if we were drawing a diagram of them, it'd just be the water molecules in there. It is not until ions, ionic compounds like sodium chloride or even the weak ones dissolve in water that you get it to conduct electricity. Now you may say, oh, wait a minute. Well, how come my bathtub if I don't want to stick my dryer in there? That's because the tap water that you're using has ions in there, okay? And that's why it conducts electricity. So just a side note, I was reading some of the assignments. Okay, so we had ionic compounds, and then we have covalent compounds. Now, covalent compounds, to refresh your memory, is a combination of two non-metals, a metal and a non-metal. Okay? Two non-metals. And so the case with ionic compounds, any of the metals that are there, sodium, potassium, any of the metals combined with a non-metal, the chlorides, the oxygen, the oxide, the phosphide, etc. Okay? The non-metals deal with just, the covalent compounds deal with non-metals. Carbon dioxide, carbon and oxygen are non-metals. Okay? Covalent compounds, with the exception of acids, do not dissociate when they're dissolved in water. Acids, as we talked about back in the acid base chapter, they're just a special case. There's a proton that when they dissolve, they dissociate into ions. They don't begin as ions, but once they get in water, they break up into ions. Okay, note the difference. Ionic compounds start off as ions, and when you put them in water, they continue to be ions. Acids start off as covalent compounds. When you put them in water, they ionize, okay? That's the difference. So within the covalent compounds, there was two types, two subcategories, okay? And so I'm going to denote them by the A and B. So when A, whatever non-metal it is bonded to A, meaning that in that bond, those atoms are the same, okay? They're the same. That gave you still a covalent bond, but it was non-polar, okay? And why is it non-polar? That's because the electronegativity, remember that property, En? The electronegativity, and that is a measure of the atom's affinity to draw electrons onto itself in a bonded molecule. Not to be confused with ionization energy, which is dealing with removing an electron from an atom, okay? So here we're talking about bonded species. And all the atoms have a negativity value. When AA are the same, then the pull is equally shared. So that bond represented by that line there between them is a pair of electrons, and those electrons are equally shared between A and A, okay? The other example of a nonpolar bond, specific example we talked about, was a bond between carbon and hydrogen, okay? That is because the electronegativity between carbon and hydrogen, by the most part, is negligible, very close to each other, and therefore they are nonpolar. Excuse me, I had a senior moment there for a second. Now, being nonpolar is important to be able to recognize that, because that's going to take us over to the intermolecular forces. Why certain things, why certain compounds, for example, boil at a certain temperature relative to another compound. Why things like honey is very viscous at room temperature and flow very thickly, if you will, compared to water. And those has to do with these intermolecular forces that we're going to talk about. But to address those, we need to make sure we understand about the covalent bond and the ionic bond. Now, when that covalent bond is with something else other than A, other than itself, okay, automatically, with the exception of carbon, hydrogen, automatically, it's a polar bond. Polar. You don't have to analyze it or think about it. Why is it polar, with the exception of carbon and hydrogen? Again, I emphasize that. Why? Because the electronegativity of one, either A or B, is always going to be much greater than the other partner, okay? So, and when that occurs, that means, here we go with the tug of war in that bond, that atom with a higher electronegativity is going to want to draw those shared electrons onto itself with a greater force than the other one, resulting in a partial charge, not to be confused with ionic compounds that have a full-fledged charge. In polar covalent bonds, they have a partial charge, something that's much, much less than the full charge, okay? And you end up with a dipole arrow, meaning in what direction the electrons are being pulled. So now that we can distinguish the two, that's going to really help us, because when we start assigning the intermolecular forces onto compounds, they're going to be dependent on the type of bond that they have, okay? Type of bond that they have. And you have to be able to look at that bond and say, oh, this is a covalent bond, okay? But it's a nonpolar bond, okay? And once we know that, we can now do a lot of relative comparison between molecules. All right, also to remember that like dissolves like. So we're gonna, when we talk about dissolving, we talk about the most polar solvent we have, and that's water, plain ordinary water. Water is very polar. And a solvent that's nonpolar would be, an example would be oil, okay? And so compounds that are polar will be more readily soluble in water than they would in oil. And the converse is true. Compounds that are nonpolar will dissolve much more efficiently in nonpolar solvents. Next time you're cooking an egg, you got butter in that pan, throw some butter, melt it down, throw some salt. Tell me if that salt dissolves. It won't, because sodium chloride is very ionic and very polar in itself. Just the fact that they're ionic compounds, ionic bonds, just makes them by default polar compounds. Okay. All right. So that's important. Ionic bonds versus covalent bonds. And within the covalent bonds, go back and remember and refresh your memory on how to distinguish between nonpolar and polar bonds. And it's not that difficult. Think of the A versus AB. A and B are totally different atoms. Therefore, we got a change in electronegativity, okay, which makes it a polar bond. AA, same atom. So the negativity is the same in both cases. There's an equal pull, equal sharing. All right. Okay, so let us go back to the chapter. So intermolecular forces. These deal with interactions with other molecules, okay? And, you know, not to be compared, not to be confused, I should say, with intra, okay? Intra, which is right here, deal with the actual bond itself. You can see right there, okay, intra. Whereas inter, INTER, deals with interactions between molecules. Some of these interactions are pretty strong. If we look at water, for example, water boils at 100 degrees Celsius, or 212 Fahrenheit. That's a reasonable high temperature. And if you look at, let's say, alcohol, drinking alcohol, ethanol, it boils somewhere in the order of 78 degrees Celsius. Now, they share a lot of common properties, okay? Water and the alcohol, they're both polar. That's why you can make a mixed drink, because they dissolve in each other, all right? But the intermolecular forces of the alcohol are much weaker than the intermolecular forces of water. And being much weaker, that interaction can be easily broken and the molecules of ethanol dissolve even more so. Another example would be acetone. We're all familiar with acetone. You ladies out there use it for your fingernail polish remover. You open up that cap and it's very volatile. It boils away pretty, very quickly. It doesn't take much energy to break up those intermolecular forces between the molecules to get those to boil away. And that's what we're talking about, intermolecular forces. The interactions between molecules, okay? Now, as far as strength, yes, there's different types of IMF interactions. Each have a relative strength compared to each other. But as compared to an actual bond, they're much, much weaker, okay? We're much, much weaker. In fact, that's what we do when we are boiling something to get it to boil. It's what's happening, those interactions that are happening right here in the dotted line, those are interactions, IMF interactions. And so as we put energy into the system, what we're doing is we're trying to break that interaction up so we can separate the molecules from each other and cause those molecules to go up into the atmosphere, okay? So that's what it is. So if we have very strong interactions, then it's going to take a lot of energy to break those interactions, and the boiling point is going to be a lot higher, okay? And we're going to use the boiling point, surface tension, vapor pressure, and some other properties. And we're going to compare molecules. Now, we can do absolute values and say, okay, this has an absolute boiling point of so-and-so, but we can take two molecules, look at them, determine what type of molecule they are. After we assign the type of molecule, then we can do a comparison. We can say that one of these boils at a higher temperature than the other one. One of these has a higher vapor pressure. One of these is a lot more viscous than the other one, okay? Things of that nature. All right. So intermolecular forces is what holds the molecules together relative to each other. okay? Not to be confused with the intra. That is the actual bond in the molecule. All right, so go back and review your polar and nonpolar bonds in molecules and so forth. That'll help you out. So bonds versus IMF, okay? So one hydrochloric acid molecule that holds the hydrogen atom to the chlorine, this is a polar covalent bond. Notice that two different atoms are bonded together. AB, example, okay? Automatically a polar molecule. Now you might say, all right, once I know that, and which direction is that arrow go to? Well, what do we know? That the chloride is higher in electronegativity than hydrogen. And so we can draw the arrow in the direction of the chloride, which means that the chloride will have that partial negative. Remember that symbol, the lowercase delta? And the hydrogen will have a partial positive. And that's why this guy, this HEL, these acids are very, what happens that electronegativity is pretty strong. So we put this in water, that causes that proton, now has a proton, to dissociate. That's the unique property of only the acids, okay? So what's holding the hydrogen chloride together is the polar covalent bond. Okay, now, when we look at the interactions with other molecules of hydrochloric acid, remember, we live in a three-dimensional world. We don't just have HCl sitting there all by itself, okay? There's molecules all around. They're all around each other. They got them below, above, and so forth on all three axes, okay? And so they're interacting. Now, you might ask, well, why are they interacting? Well, think about this for a moment. Because of the polarity of the molecule, like we just drew up here in the top left, realize that we have a partial positive on the hydrogen, right? And we have a partial negative on the chloride. Well, guess what? We have an interaction going on there because we've got the positive being attracted to the negative. And that's what results in this interaction right there, this intermolecular forces. And so dipole compounds will always have some type of a interaction, a fairly strong interaction as compared to nonpolar. Nonpolars will have one. We'll talk about that in a second, but not as strong as a polar covalent compound like HCl, because it has a permanent dipole. That dipole that has been created, okay, that dipole in there is a permanent dipole. Two poles, di being two, right? It's permanent because of the nature of the beast, because you got the chloride bonded to the hydrogen, okay? When we get to nonpolar bonds, we're going to talk about an induced dipole. It creates a temporary dipole. All right. So there are four types of intermolecular forces. And these are interactions between the partial and the partial negative charges between molecules, okay? Type number one, which by the way is the weakest of these four types. We call those the London Dispersion Forces, or LDF, okay? Number two is a dipole force, okay? Just like the example we just did with the HCl, it's a dipole. You can really go to infinity. Dipole. There's like little magnets all lined up, okay, because of the negative and positive charge, okay? It's like putting a bunch of batteries in series. That's the second type. Then we have a very special type of polar bond, and we call that hydrogen bridging force. And it's special because it only occurs to certain types. That's when hydrogens are bonded to certain atoms. that, yes, it is a dipole-dipole, but because of the nature of the beads, they have an additional force. It's a little bit stronger, and we call that hydrogen bridging force. The old terminology used to be hydrogen bonding. They're trying to get away from that calling it hydrogen bonding because it's not a bond, okay? It's an interaction between molecules due to their dipole, okay? And then the fourth one is called the Ion Dipole Force. Now, think about this one. It only pertains to examples where you have water and some ionic compound, CPD, ionic compound, okay? Only for that example. So, which is kind of separated from that. So if you look at a question that you may be asked, and they may be talking about sodium chloride dissolved in water, what interaction you're talking about? Well, the only option you have is number 4, because we're talking about ion dipole forces. And to have an ion, you have to have water, which you have to have an ionic compound. Okay? All right, so let's continue. All right, so let's talk about dispersion forces. These are temporary. And the important part is this. For any molecule that is nonpolar, okay, that's why as soon as you look at the molecule and you recognize that it is a nonpolar species, then the only force that it deals with is the dispersion force, the London dispersion force. Okay, so you got to learn to recognize where there's polar and nonpolar. Okay, now the thing is that these forces are, as I stated, temporary. They're not permanent, like the case with the dipole. Okay, and what's happening is electrons kind of get pushed away. The classic example of what's happening here is that, I may have talked about this way back when I talked about a balloon, you rub a balloon onto your head, okay? Well, what you've done is when you're rubbing a balloon onto your head, you have transferred those electrons on your hair to the surface of the balloon. Then when you bring it down to your chest, okay, remember that we got electrons all around us, okay? So as I bring that balloon loaded with electrons, I have a negative charge onto your chest, then those electrons on the surface of your chest get pushed into your body, resulting in a partial positive area on your chest. Well, if you got a partial positive area, the balloon is a partial negative area because it's loaded with electrons. What's going to happen? That balloon is going to stick to the surface of your chest. Try this at home, okay? Rub your head with a balloon, put it on your chest, it sticks. But it won't stick there forever. It's temporary. Eventually, the electrons reestablish themselves and get into a more stable state, and that balloon falls off. But what you have done by bringing that balloon in here, you have induced a dipole. The other examples of polar covalent bonds have a permanent dipole. Non-polar compounds have a temporary dipole. They have an induced dipole, if you will. Okay? They're just temporarily being pushed to one side. Oh, and yeah, you see these in gases. There's very little interaction between them, but very small interactions. Normally, the bigger the molecule, the more electrons, the more London forces. So what that means is this: if I'm comparing two nonpolar species, and I want to know who's got the stronger London force, well, obviously, what they're telling you here is the bigger molecule would have more electrons, therefore it will be stronger with respect to the London dispersion forces. Okay, that's all that means right there. And this, let me clear this up here. This kind of shows you what's going on. Yeah, so you're getting two nonpolar species coming in, like a diatomic molecule. They kind of come close to each other. Electrons are kind of pushed away. We generate what is generated as temporary dipole, if you will, a temporary partial negative. Remember, this is just temp. Okay, but the result is they do create a interaction and you create a force, which is called a London dispersion force. And they're very weak, okay, compared to the other forces because they're temporary, okay? Temporary. And if it was bigger, if I was going to compare another molecule that was, you know, this big, obviously these two would be a lot bigger, stronger London dispersion force than the ones in green, simply because they're bigger, more electrons. Okay. Now, dipole forces. We just talked about London dispersion. Dipole forces. Now, these have a permanent dipole, okay? Like hydrochloric acid. They have a permanent dipole because of the nature of the beast of that bond. One of those atoms has a higher electronegativity than the other, so that sharing here in the chloride, it's going to pull those electrons toward itself much greater than hydrogen is. So therefore, it results in a partial negative charge, or force, I should say. Well, it does have a partial negative charge. Let me state that right here, which then interacts with the partial positive side of another molecule, resulting in this dotted line here, this interaction. And of course, we just drew this in 2 dimensions, but keep in mind, this is happening 3-dimensionally, okay? Give me 1 second. Okay, sorry, I'm back. Well, I lost my pen for my, give me another second, I apologize. Found it, fell off. Okay, so here, interaction number 2, dipole forces. That deals with molecules that have a permanent dipole and they interact with each other. Okay. Let's do another one. Here's some more information about dipole forces. They're stronger than London forces, and it's required that the molecules must be polar. It's a requirement. Now, hydrogen bridging forces. Yes, they are a dipole, but they have an additional interaction because, and this is only for hydrogen that is bonded to nitrogen, oxygen, and fluoride. Only for those examples, okay, that you have what is called the hydrogen bridging force. And here's an example right here with water. Water has hydrogen bridging force because there's a hydrogen bonded to an oxygen. One way to remember it, NOF, I don't know, not on file, maybe that helps. Nitrogen, oxygen, and fluoride. Hydrogen bonded to those three elements. This force right here is fairly hefty, pretty strong. Now, it's much stronger than the dipole interactions, and which is much stronger than the London dispersion forces. So the hierarchy is hydrogen bridging forces being the strongest, followed by the dipole, and then the London dispersion forces being the weakest of the three, okay? Now, the ion dipole, we can't, that's like apples and oranges, because in this case, we're talking about molecules by interacting with themselves. Has nothing to do with water that's interacting here. Whereas the ion dipole interaction deals with 99% of the time is water, which means we're dealing with an ionic compound. Okay, so hydrogen bridging. Gonna say very strong, much stronger than dipole, but still weaker than ionic or even a covalent, much weaker than a covalent bond. Again, we're not talking about bonds within the molecule, not about intra interactions. We're talking about inter interactions, and those are interactions with molecules amongst themselves. Okay. Finally, the ion dipole. You can see here that we need an ionic compound, and we need something that's polar, and that's 9 times out of 10, 99.9999% of the time we're dealing with water. And this diagram here, you can see it shows you how the sodium ion is solvated and surrounded by the water molecule, specifically the oxygen of water, okay? Because the oxygen has a very, has a strong partial negative, right? And they're gonna be attracted to the positive charge of the, right in here, this interaction going on here. I'm gonna just kind of, not a bond, but it's very strong interaction. And if this was sodium chloride, guess what? The chloride will be out here and it will be interacting with the positives of the protons, okay? And that's what's happening to how the salts are solvated and dissolved in aqueous solution, specifically water, okay? Specifically water. All right. Very strong interaction there. Well, let's summarize the forces here versus the bonds. Bonds. We have ionic bonds, which hold, as I spoke before, metal and non-metal. Okay, that's what attracts the ions together. Then, of course, we have the polar covalent bonds, which we have unequal sharing between different. And that's the key, because I find that students still have a challenge with that. The key word is different, okay? And so in that case, would be like an example of A plus bonded to B. And because of the different atoms, they have a different electronegativity. So therefore, we're going to have a polar bond compared to nonpolar bonds where they have the same nonmetals, which could be, A and A, or it could be B and B, okay? And so if you think about it, all of the diatomic molecules that we have no fear of ice cold beverage, would have nonpolar covalent bonds, and anything with carbon hydrogen, the hydrocarbons, for example, all would be nonpolar. Okay. All right. Now, with that, we look at the forces. London forces. Only those molecules that are nonpolar, that's the force they have. Okay. The dipole, first of all, they have to be a polar molecule. So we're talking about covalent compounds here, right? Polar molecules. And the hydrogen bridging is only those polar molecules that have hydrogen bonded to nitrogen or oxygen or fluoride, okay, only. They have the hydrogen bridging force. And then we have finally the ion dipole force. It is a specific ion, which comes from an ionic compound. And a polar molecule is a solvent. And like I stated, the majority of the time, we're dealing with H2O, water. Okay? All right. So let's continue here. Let's go through this. Now, this is where we kind of put everything together. Now, go back and refresh your memory on the Lewis dot structures. So you thought, oh, I'm done with Lewis structures. I won't see them again. Well, we need them now to figure out the structure and geometry of the molecules, because that's going to tell us whether that molecule is polar or nonpolar. Remember the criteria to determine whether a molecule is polar. If a compound has all nonpolar bonds, then it's nonpolar, right? Pretty straightforward. If a compound has polar bonds and they do not cancel out each other, then you have a polar species. If you have polar bonds and they cancel each other out, as far as that polar bond, then it's nonpolar, okay? And in order to determine that, we sometimes need to draw the Lewis dot structure. Okay, let's take a look at carbon dioxide. We had done carbon dioxide a while back, and I'm just going to draw the formula that we came up with. We came up with oxygen, double bonded to carbon, double bonded to carbon, and those were the lone pair, okay? Now, we know that when we look at carbon and oxygen bond, it is a polar bond. Two different elements, automatically polar bond. So then the next step is find that arrow, the polar arrow, which direction, the dipole arrow, which direction is it going? Well, we have to determine who is more electronegative. Remember, we use fluorine as our benchmark. Fluorine is the most electronegative atom on the periodic table. And so if we are comparing two atoms other than fluorine, okay, to determine who's more electronegative, we determine where on the periodic table who's closer to fluorine. In this case, oxygen is closer to fluorine. Therefore, oxygen has higher electronegativity, higher En. What that means is that that dipole arrow goes from carbon to oxygen. Oxygen's pulling the electrons at a much greater strength than carbon is. So that puts a partial negative on the oxygen and a partial positive on the carbon. Keep in mind there are two bonds. And the other carbon-oxygen bond also is polar, and that arrow is going in the opposite direction. Well, these dipole arrows are what I talked about them. And they're called vectors. Which basically just means by looking at them, I can add them or subtract them. So the one on the left is going in the negative direction. The length of the arrow roughly represents the magnitude of that force. And I'm trying to draw them about the same size to show you the magnitude is the same. So one's going to the negative direction, one's going to the positive direction. The result is they cancel out, which means that carbon dioxide is nonpolar. Okay? Carbon dioxide is strictly nonpolar. With that, we can very quickly determine what force it's dealing with. And that would be the London dispersion force, because the criteria for a London dispersion force is it must be nonpolar. A polar molecule cannot have London dispersion forces. Okay, let me put that out there. Okay? A polar molecule cannot have London forces. Let me restate that because I'm sure it'll come back and bite me. The probability of having London forces is low. Can it have London forces? Yeah, but very temporary. Okay, let's look at PF3. Well, if we go through the Lewis dot structure, okay, and we add up the formulas and do all that, guess what we come up with? We come up with a formula that looks like this structure. Okay, just like ammonia with a lone pair in the central atom. Okay, and that's an B3E. You can look that up. Okay, and way back when I said, when you got a lone pair, when you do the Lewis structure and you come up with a lone pair in the central atom, that's all she wrote. You have a polar molecule because those electrons take up a lot of space, and this dipole on the phosphorus fluoride bond, if this was tetrahedral, they would all cancel out, but not here because the lone pairs take up a lot of space and they push that bond angle down to be much less than 109.4. Now, if let's say we have carbon, and I'm going to try to draw it with a little bit of geometry, tetrahedral, tetrafluoride, carbon tetrafluoride, okay? This wedge bond comes out of the face. The two fluorides of the solid line represent on the X and Y axis. The fluoride with the hash dotted or the hash marks, it goes behind the screen. The wedge goes up in front of the screen. So three-dimensionally if you can. Now, yes, they all have polar bonds, and they're all pointing toward the fluorides, obviously, because the fluorides are the most electronegative. So you would think, oh, polar bonds, polar molecule. That's not the case. Because in this configuration, the tetrahedral, when you have polar bonds all around, 4 of them, mathematically, they all cancel out. The result is you also have NP, nonpolar. Okay? Now, the moment, and this is important, okay, put this in long term. If I were to replace one of these hydrogens with anything else, no matter what, other than fluoride, anything else, I will create, if I were to, let's say, maybe even chloride, put a chloride in there, okay? Well, guess what happens? Now I have a polar molecule because now the magnitude, remember that dipole arrow? There is a magnitude represented with that polar bond. and depends on the force, who's got the electronegativity, higher electronegativity. Yes, there's a polar bond between the chloride and carbon. Yes, there is, but the magnitude of its arrow is different from the magnitude of the carbon and the fluoride. The result is that those four bonds do not cancel out. And so we end up with a polar bond, okay? Just by simply changing one of those. All right, so now going back to PF3, we have a polar bond. And so now we have to figure out, well, strongest intermolecular force. It can't be London, and it can't be ion polar, right? Ion, there's no ions involved here, so it's not those. So we have to decide whether it is dipole-dipole or hydrogen bridging. Well, it can't be hydrogen bridging. Why? Because there's no hydrogen involved here. Therefore, the only other force left over is the dipole-dipole. Okay? See how I went through that scenario? Figure out what is the strong intermolecular force. Okay. I'll repeat it one more time. It's crucial. It helps you. That's why I emphasize a systematic approach for all these chemistry problems. All right. So we didn't know what it is, but we figure out it's polar based on the electron dot structure. And we ended up with a couple of lone pairs in the central atom. Automatically, I got a polar species. Okay. Now, I got to figure out, of those four forces, which one is involved here. The fact that it's polar eliminates the London forces. Get that out of the picture. The fact that there's no ionic compound here, or even mention of, say, an aqueous system, we can eliminate that ion dipole force. So that's two. So the only two forces left, there's dipole-dipole and the hydrogen bridging. The hydrogen bridging requires hydrogen, hence the term hydrogen, right? There's no hydrogen here. It's phosphorus and fluoride. So we can eliminate that. So the only thing left over is the dipole-dipole. Okay, good. All right, so now we have the species here, HF, hydrofluoric acid. Okay, A and B, dipole, we have a dipole. Okay, which means it's polar, right? A and B example. All right, so we go through the same process. It's polar, can't be London. No mention here of aqueous systems or anything like that. It can't be the ion dipole, eliminate that. That leaves dipole-dipole and hydrogen bridging. Well, it could be dipole-dipole, right? Because we have a polar molecule, right? But we go one more step. Check out the hydrogen bridging. What is the requirement? One, we got to have hydrogen and either or nitrogen, oxygen, or fluoride, which we have. And so that takes precedence. So you have a hydrogen bridge force with HF. All right, carbon, next one, CH4. That's the formula for methane, tetrahedral. But look at the molecule again. It's a hydrocarbon, nothing but carbon and hydrogen. Okay? That's it, carbon and hydrogen. So that means we have a non-polar species. Remember all the diatomics, right? Plus carbon, hydrogen give you a non-polar species. Also, if it's a polar bond and they don't cancel each other out, and they cancel each other out, I should say you got a polar, non-polar species like carbon dioxide, right? And so we have non-polar, and that's all you wrote. Once you figure out it's non-polar, there's only one force, and that is London. Okay. All right, finally, the last one. The fact that you're dealing with an ionic compound, okay, and it is an aqueous system, okay, it's basically, you know, it's not really polar or non-polar. It's already, by default, the fact that it's ionic, it's an ionic in polar water because we got AQ. And therefore it has nothing to do with London forces, nothing to do with dipole-dipole. nothing to do with hydrogen bridging force. And that's the only force involved there. And that is the ion dipole. Okay. All right. Any questions up to this point? Okay. There is this thing called Kuhn's law. Okay. All right. Don't need to know too much about this. I just want you to look. We'll look at the equation and we'll go through some examples. Okay. But basically, what this says is that the attraction between two charges is proportional to the charge magnitude. In other words, if I got two small charges, you have X amount of force between them. But if I increase the charge, make them bigger, maybe it can go from a +1 to a +2 or -1 to a -2, the force increases proportionally, okay? But it is inversely proportional to the distance between the charges. Inversely proportional. As when we say that something's proportional, when we're looking at relationships between variables, when one variable goes up and the other variable goes up the same, and it goes in a positive direction, that is proportional, okay? Same is true. If one variable drops, the other one drops, that's proportional. Now, when one variable goes up, but the other variable drops, then we call that inversely proportional, okay? That's what they're trying to say here. So ideally, what you want, you study hard, you get good grades, right? That's directly proportional. But if you study hard and you get bad grades, that's inversely proportional, and you don't want that, right? Okay. So this is what they're talking about. Now, what happens here is this. All right. So we got this crazy equation where the force is equal to KE, which is simply just an equation, a constant, okay? And then Q1 and Q2 are the charges. So not worry too much about that right now, but I'm just going to deal with the R. R is the radius, and that's the distance between two charges. And so what I can do, I can simplify that equation. I can combine the K and the Q's, and I'm just going to very quickly just rename them as A. A represents all those variables, and I'm going to keep R squared, okay? So those A, the Q, the two Q's and the K are going to stay constant. And the only thing I'm going to change is the radius, and then look at the force. All right, so we're going to start off with a radius of, let's say, let me check something here real quick. Okay. Okay, so let's start initially with a radius of 1 unit. It could be centimeter, inch, but just say 1 unit. And so if we do the calculation and we say that R equals 1, obviously, right? 1 times R squared, 1 squared times 1 squared is 1. And so the force is equal to A, whatever A may be. That's Q, the two Q's and the K. All right. Now, let's take the second scenario. Let's double the radius. Whereas at 1, now we're at 2, okay? And so what happens there? So now force becomes A divided by 2 squared. And that means that A is divided by 4, or 1/4. So the force, by doubling the distance between the two charges, a simple thing is doubling the charge, we have decreased that force by 1/4. Okay, the force dropped by 1/4. And it makes sense when you think about it. You have two magnets together, and let's say you got the north and the south coming together. You can feel that force as you bring them closer together, get stronger. as they try to attract to each other, or the other direction trying to repel. You can feel that force very strongly. And as you move away, that force diminishes. Force is still there, but not as much. Now, if you go the other direction, and let's say you go, what happened here? A little bit of a trouble here. Okay. Now, let's say you go the opposite direction. And now R is equal to half of what you started. So now R is 0.5, right? And so now you have force is equal to A divided by 0.5 squared, which is A divided by 0.25, which means that A increased by a factor of 4. And so where you are at 1 centimeter, you have an X amount of force. As you double the distance, the force diminishes by a quarter. But if I bring the force in closer by half of what I started, 0.5, I increase that force by a factor of 4. And that's what we're talking about with respect to the forces inversely proportional to the radius squared of the two charges, okay? A little bit extra math, but that's what we want you to take away from that equation. All right, so sometimes you're going to have questions like this. They're going to ask you, they're going to say, what holds the atoms together in one ammonia molecule? Now, it's crucial that you read the question carefully, okay? Because that's going to tell you whether you're dealing with inter forces or intra forces, okay? So more than one molecule, we're dealing with inter. One molecule, we're dealing with intra. And that's the key right there. What holds the atoms together in one ammonia molecule? So what's holding that together? That would be polar covalent bonds, okay? What is holding the sodium ions in water? And we're talking about sodium ions. So that would be the Ion Dipole Force, because we're dealing with an ion and we're dealing with a dipole force, which in this case is water. Water does have a dipole and has specifically hydrogen bridging force. Here, what is holding 3 HCl molecules together? Keyword 3. So we're dealing with interactions with molecules with each other, okay? And that would be dipole forces. Now, you might say, well, wait a minute. You have hydrogen. We know it's a dipole. Why not hydrogen bridging? Well, remember, hydrogen bridging only pertains to hydrogen to nitrogen, hydrogen to oxygen, hydrogen to fluoride. Okay, so here we're dealing hydrogen to chloride. So that would not be hydrogen bridging. What is holding the ions together in salt, sodium chloride? Well, they're talking about sodium chloride, table salt in the salt form. What is holding them together? They're ionic bonds. How do I know that? Because ionic bonds are metal, non-metal. Sodium is metal, chloride is non-metal. What is holding what is holding 4 H2O molecules together? Now we're dealing with we're dealing with other molecules. So we determine that, okay, H2O, It's polar, extremely polar. Plus, it's hydrogen bonded to oxygen. Therefore, we have hydrogen bridging forces. What is holding nitrogen gas molecules to each other? Okay, well, nitrogen gas, these are diatomic. Okay, so being diatomic, nonpolar. Nonpolar, London forces. Okay. And then what is holding the oxygens together in an oxygen gas molecule? So we're talking about within the molecule. So we're dealing with intra forces. What type of bond? And they're saying oxygen gas. So it's a nonpolar covalent bond. Okay. And then finally, what is holding two ammonia molecules together? We've done a lot of ammonia, so hopefully you recognize that. If you haven't, you may want to memorize it. It's NH3 ammonia, okay? And if you do the Lewis-Dot structure on that, you come up with this structure with two lone pairs in there. All right, polar, okay? So we know it's polar. Once we know that, then depends which one. It's not London forces because it's polar. It's not ion covalent because there's no mention of aqueous system here. So it's either dipole-dipole, hydrogen bridging. Can't be dipole. Well, it could be dipole-dipole. However, we got hydrogen bonded to nitrogen. So that tells us that is hydrogen bridging. Okay. There's only three molecules. Remember that for hydrogen bridging, there's only three types of compounds. And those are given, I got here in a circle: hydrogen, nitrogen, hydrogen, oxygen, and hydrogen fluoride. Okay. So basically, to summarize the Imf interactions, first of all, we determine if it's covalent, all right? If it's nonpolar, go to the left. It's all she wrote. It's all London forces. Okay. If it's polar, we go to the right, and through a process of elimination, depending on the question being asked and what are the factors, is one of those three: dipole-dipole, hydrogen bridging, ion dipole. Remember, ion dipole deals with aqueous systems. Hydrogen bridging deals only with hydrogen bonded to nitrogen, oxygen, fluoride, and then all the other ones are simply dipole-dipole. Okay. We're going to explore a little bit, talk about, I'm going to just go a couple more pages and then I'm going to try to explore here, but we're going to talk about what is called vapor pressure and boiling point, surface tension, and viscosity. Okay. Well, with respect to vapor pressure, let me get a bottle here. 1 second. Okay, if you were to take, let's say, a soda pop bottle, okay, and here's my bottle, but this is water, but let's assume that this is soda pop, because that really shows you the pressure. Obviously, that bottle, closed bottle, is not full all the way to the top. So there's a bit of empty airspace on top here, right? If we were able to put a meter on that space and measure the pressure of that vapor in there, we would get what's called the vapor pressure. All right. Now, vapor pressure goes up pretty high if you take a soda bottle and you shake it, right? If you shake it up, that carbon dioxide comes out of the solution and goes up in the area of empty of air up here. And if this was a meter, it would pressure would go up, correct? Until such time that the carbon dioxide would equilibrate and go back in. Now, think about this. If these molecules of water or whatever liquid you have in the bottle, if they hold on to each other very tightly because their intermolecular forces are strong, then that vapor pressure will not be very high because they're holding on to each other very strongly, okay? The converse is true, meaning that if this interaction here was, say, weak relative to the forces we're talking about, then there's going to be more liquid molecules being pushed up into the vapor, and their pressure will go up. Okay? And so let's say acetone. If we had a bottle of acetone versus water, we will find that the acetone, because we know it's very volatile, right? I'm sure you've used it or seen it or smelled it when you open the container and you smell acetone or fingernail polish remover, okay? Because the interactions with the molecules with each other are not very strong, so it's very volatile. So if we had a closed container of, say, acetone with a cap in that meter, that vapor pressure would be relatively higher than just water, okay? And so that tells me that because the vapor pressure is higher compared to water, that the intermolecular forces of acetone are much weaker than the ones than water, okay? And that's because these interactions, when we heat something, either with direct heat or with just the warmth of our hand, if those forces are weak, the warmth of our hand will cause these molecules to vaporize, okay? Same thing is true with boiling point. If a liquid has very strong intermolecular forces, then their boiling point is going to be much higher relative to another compound. And so water, for example, like I mentioned earlier, boils at 100 degrees. And if we compare that to ethanol, which has also polar, but its intermolecular forces are a little bit weaker than water, and that boils at 78 degrees versus 100, okay? Surface tension, again, that's a measure of how liquid beads up when it's on the surface. Yeah, I'm sure you've seen this. You know, you just go wash your car and you clean it up and you wax it, okay? And then you add you drop a little water and it beads up. That's surface tension. That's how the liquid beads up. And so molecules that hold on to each other much greater will have a higher surface tension than those molecules that do not. They'll be spread out. Their beads will be a little bit flatter than others that will be a little bit tighter. And viscosity, okay? Viscosity is just a measure basically of how thick or how a measure of the flow, or really technically the resistance to flow, a solution would be. A classic example would be water versus honey. We know that honey is very thick. And if we were going to do a race to see who can empty itself in a cup quicker, obviously the water is going to win because the honey is very viscous. And that's again because its intermolecular forces are much stronger than the one with water, the forces with water. So it flows. But think about this. How can I make honey flow much quicker? Anybody have an idea? You know, I got honey. I want it to flow quicker because I need to pour it out of a container into something else. How can I make it flow quicker? What would you do? What would your intuition tell you to do? Heat it up. Exactly. You heat it up and think about this. When you're heating it up, what you're doing is you're breaking up the intermolecular forces between the molecules and allowing it to separate from each other, not to interact with each other as strong as if they were at, say, room temperature. And yeah, all of these here, all these properties here, you can increase by playing with the temperature. But we're not going to do that. We're just going to compare them relative to each other. That's all we can do. Remember this. If we start comparing vapor pressure, boiling point, surface tension, viscosity, all we can do is, okay, compound A versus compound B. Who's going to have the highest vapor pressure? Well, to determine that, we first determine, is it polar or nonpolar? If it's nonpolar, then we have some information. If we polar, then we determine, okay, is it hydrogen bridging or dipole-dipole, okay? That's what we're dealing with. And we're dealing with the three forces, not the last one, the Ion Dipole Force. When we do comparison, we're dealing with just the three, the London forces, dipole-dipole, and hydrogen bridging. Oh, you're right. Thank you. Sorry about that. I get a little carried away. All right. Well, let me stop it here, and let me see. What's slide 21? All right. And so, like I said, next Tuesday, I'll send an email out, and we'll start every Tuesday from this point forward, which is going to be roughly 3 Tuesdays. Starting next Tuesday will be a study day. So look at your stuff, see if there's something you don't quite understand. Look at the old exams, bring them to class. We'll go over it. You can share, if you got them digital, put them on, you can share your screen and we can all see it. The other aspect too, there are some assignments that were from way back when that I left with no score there. Some of them from like January, February, and I finally went back in there and I put a 0 in there. And so you might be wondering what happened here. Some of those assignments, whatever you submitted, like a file, can't open. Some people have turned in files with an extension of HEIC, and Canvas can't open that thing up. Heck, I download it and I try to open it up myself and it won't open up. So, either get a JPEG, PDF, number one, JPEG, and then bitmap, I guess, or JPEG if you can. When you turn it in assignments. Anyway, if it has a 0, you can still go back and submit a corrected file. Take a look at it, okay? Otherwise, it'll stay a 0. Okay, any questions? All right, you guys